Okay, we have talked about first order systems, second order systems, and today we will be talking about a central concept in controls, which is stability. Okay. So far we had buried the concept of stability under the rug, and we were considering systems that had oscillatory outputs, but they were all bounded. Okay. Let me motivate the concept of stability using a simple idea. So consider that I have a system 1 over s plus p. I give it an input 1 over s. The output is 1 over s plus p. Okay, so it's a first order system. I give it a step input. I get this output, and I can actually write it as 1 over p, 1 over s minus 1 over s plus p. Okay. What's the inverse Laplace transform of this? What would be the inverse Laplace transform of this? Any thoughts? 1 over p, 1 minus? Yeah. Okay, for t greater than equal to 0. So if p was positive, okay, I want to plot these curves for the case when p is positive and when p is negative. Okay, so when p is positive, that's the case we have considered several times in this class, and we have learned that if p is positive, this term decays to 0 as t goes to infinity, because e raised to minus some positive number multiplied by infinity is equal to 0. And so the step response looks something like this. Okay, and this would be my 1 over p value. What happens when p is less than 0? I want you to think what happens when p is less than 0 in this case. Sorry? Infinity or minus infinity? Minus infinity, okay. So it starts from 0 and then it goes to minus infinity, okay. So when p is less than 0, the response goes to minus infinity, whereas when p is greater than 0, it settles to some steady state value. Okay, and 0 is that threshold. Zero is that threshold. What happens when p is equal to 0? So we can't apply this result. When p is equal to 0, then y of s equals to 1 over s square, which implies y of t is equal to t. Yeah, y of t is equal to t for t greater than 0. But this also goes to infinity. When p is equal to 0, a step input goes to infinity. When p is greater than 0, oh, wait a second. Am I right in saying when p is less than 0, it will go to minus infinity? Oh, because you have a negative p here, so it will go to plus infinity. So when p is negative, this p is also negative, so it will go to plus infinity, not minus infinity. So it will go this way. Sorry about that. So it's going to look like e raised to negative pt minus 1 over minus p. That's what it's going to look like. Okay, so I neglected that 1 over p term, which is going to be negative in this case, so it's going to go to, negative, Okay. So let's recap once again. When p is negative, when p is positive, the system converges to some steady state value. If p is equal to 0, y of t grows linearly with t. When p is strictly negative, the response goes all the way to infinity. Okay. So far in the class, we've talked about the outputs that are temperature, pressure, some velocity, state, position, things like that. What does it mean for something to go to infinity? What does it mean for temperature to go to infinity? Or what does it mean for position to go to infinity? Any thoughts? Sorry?
Explosions.
Explosion. Okay, that's a good word. Explosion.
It's not going to be stable, right?
Sorry?
It's not going to be stable.
It's not going to be stable. So what does it mean for something to be stable? What does it mean for something to be explosive?
Feedback.
There's no feedback here. Okay, so I'm not talking about feedback. It's a system where in some cases the state goes to a steady state value, and in some cases the state explodes. Okay. Any thoughts? What should be? So we kind of understand by looking at these examples that there is some notion of stability, and we want to capture that mathematically. Yes.
If it's a bounded input or a bounded output.
Bounded input, bounded output. Okay, so is 1 over s a bounded input? It's always equal to 1. Okay, so it's bounded by 1. But look at the output. Is the output bounded? Yes. Is the output bounded? No. Of course no. Okay, it's explosive. All right. So that's the concept of stability. If you give it a bounded input, the output also has to be bounded. Okay, that's the notion of stability that we'll be using.
I have a question. When the p is 0, how did we get y over s is equal to 1 over s squared?
So this is 1 over s. You give it an input 1 over s, the output is going to be 1 over s square. Okay. So good that you mentioned the word explosive, because that's an excellent example of an unstable system. Okay, so you have gas in a container. You give it a step input, which is just a spark, and then enjoy the show. Okay, it's an explosion, right? So the temperature goes very high. It doesn't go to infinity. Okay, it goes very, very high. So infinity is just an abstraction. It's a mathematical abstraction in control theory, and infinity means the system blows up. Okay, and that blow up will mean that something becomes so high that the system is no longer useful. Okay, so let's consider another example of nuclear reactors. We all know how nuclear reactors work. You put one neutrino on uranium-235, it disintegrates into smaller atoms, and then it emits 3 more neutrinos. Well, not neutrinos, neutrons. Then those 3 neutrons collide with other uranium-235 atoms, and then it disintegrates, and so on and so forth. It leads to an explosive, uncontrolled growth of chain reaction that leads to explosion. Okay, and that explosion also means that your state is going to infinity, and of course it never reaches infinity because you have a finite mass of uranium, but But infinity is just an abstraction. It means that things become extremely large, okay, too large. And that's the notion of unstable system. Now, just because the system is unstable doesn't mean it's bad, as long as you have a way to control the system, right? So in the case of nuclear reactors, we use graphite rods or some heavy metal rods in order to slow down the speed of neutrons in order to not let the chain reaction grow uncontrollably. And so in that case, instead of getting an explosive output, so the system inherently is explosive, okay? But we use controls intelligently in order to control the output and make sure it reaches some sort of steady state. Okay, same thing happens for gasoline. So gasoline is explosive, okay, but we limit the amount of gasoline flowing into an engine, and then we give it a impulse input, which is a spark, and then we convert it into mechanical energy, which drives our car, which drives buses, trucks, so on and so forth, okay. The other important thing to notice is when you talk about unstable system, and if something is going to infinity, then it means some form of energy is getting converted into some other form of energy or some other physical quantity, right? So in the case of gasoline, the chemical energy converts into heat energy. In the case of nuclear reactions, the atomic energy converts into heat energy or some other form of energy.
When you talk about system stability, does it always have to be with respect to like a certain input? Because
bounded input.
Okay.
Yeah. So you give it a bounded input, your output has to be bounded.
Are there some inputs where it explodes and other inputs where it doesn't explode?
Well, if you give it a ramp input explodes. It's not a bounded input.
Are there some inputs that are bounded?
Yeah.
That could cause the output to be unbounded?
That's exactly what's happening. Exactly what happens in a nuclear reaction or in the case of gasoline kept in a container, right? Bounded input, you just give it a spark to a can of gasoline, and it's going to lead to an uncontrolled reaction, in which case things are going to explode, okay? So that's a bounded input, which is an impulse input, and it leads to unbounded output, which is death and destruction, okay? So that's the notion of instability, okay? Does that make sense?
Yeah. So for every input.
Bounded input.
Every bounded input. It doesn't
Yeah.
matter what.
Yeah. You can give it a sinusoidal input. That's a bounded input. You can give it a sawtooth input. So input that goes up, then goes down, then goes up, then goes down. That's a bounded input, and it shouldn't lead to unbounded output. Okay. So now, in many cases, so for instance, in the case of an LC circuit, okay, so not RLC circuit, just LC, we saw that you give it an impulse input and it goes through oscillations, right? If you give it a step input, it goes through oscillations again, right? But it doesn't blow up, okay? So it just goes through oscillation, doesn't blow up. Those are known as marginally stable systems. Okay, marginally stable means that you give it a bounded input, you get a bounded output, but the output doesn't really converge to something. Okay, it just oscillates. So we have three concepts of stability. Well, not three concepts. There's just one concept, and then a refinement called relative stability. So that's what we want to talk about. Okay, so a stable system is the one that gives bounded output for every bounded input. And we have a famous result, let me call it a theorem. A system is stable if all poles are in left half open plane. This is equivalent to saying that real part of poles should be less than 0 for all poles. So a system is marginally stable if some bounded input give bounded output, other bounded inputs could give unbounded outputs. Okay. So that's known as marginally stable system. So this happens when real part of some pole is equal to 0 Okay, so even if you have a couple of poles with real part equal to 0, then it will lead to a marginally stable system, which means for some inputs it will give you bounded input. Well, for some bounded input it will give you bounded output. For some bounded inputs it will give you unbounded outputs. Okay, so I give you a system transfer function g of s, okay, and I ask you to draw the pole 0 diagram, and you draw the poles as you have any number of poles in the left half open plane. So open means that this imaginary axis is not included, and left half means this is my left side and this is the left half open plane, okay, without the imaginary axis. So if you look at all the poles and you look at the real part of the pole and they are all negative, which means they lie this side of the axis, then it means it's a stable system. Okay? If you have, so this is stable. I don't really care about zeros, okay? So 0 could be anywhere in the complex plane. I have absolutely no problem with that, but the poles have to be in the negative should have negative real part. Then I have some systems with poles on the imaginary axis and this is marginally stable. Stable systems. Okay, so LC circuit, so RLC is stable system, LC is marginally stable system, and then you have unstable system where you have at least one pole in the which has a positive real it has a pole with a positive real part. Yes.
What's an example of an unstable system?
Fighter aircrafts.
Fighter aircraft?
Yeah. Okay. So if you look at passenger aircrafts and assume that the engine doesn't work, the passenger aircraft will slowly coast down to the ground. I mean, it might crash, but it will coast down to the ground. And the excellent example was, I don't know if you remember, but in 2010 or 11, a United Airlines flight landed in Hudson River because both the engines, so there was a flock of bird flying and it hit the aircraft, so all the engines stopped working, and then the pilot carefully coasted down and then landed in the Hudson River, and nobody was actually hurt in that entire incident. Okay, so that's the example of a stable system, because even if the engines are off, you're able to land gracefully on the ground or in water. Now, unstable system, which means like a fighter aircraft or a supersonic aircraft, they are by design unstable because it leads to better maneuverability. You can twist and turn and do lots of different things easily. But if there is a loss of power at the engines, it might just fall off the sky, just like this. Okay, so it won't coast down. There will not be unless there are many control surfaces which allows you to carefully manage the uncontrollable, not the uncontrollable part, but carefully manage the instability part. If you don't have those auxiliary power units, then you will just fall out of the sky. Okay, that's an example of an unstable system. Nuclear reactions are also unstable as long as, I mean, if you don't put the control rods in, it's an unstable reaction. Okay. Yeah, so those are prominent examples of unstable systems. There was a hand, yeah.
When we look at stability, are we only looking at like the transfer function? Like when we talk about poles, are we talking about just looking at like the transfer function?
Yes.
So no input at all?
No, so stability is the property of a system, not the property of the input.
Okay.
So if you have transfer function and the transfer function has negative real, so all the poles in the transfer function have negative real part, then it's a stable system. Okay. Now if you have unstable system, you can use feedback to make it stable, which is what we do in a fighter aircraft, for instance, or in the case of nuclear reaction. Okay, we use feedback control in the form of control rods in nuclear reactors, or in the form of ailerons and so many other control surfaces in the case of fighter aircrafts. Okay, to make it stable, but otherwise they are inherently unstable system. Yes.
So like, say you have like a big block diagram, so not each individual block could have like unstable.
Yes.
That block
Yes.
unstable, but if you reduce it down.
That's right.
To one block.
That's right.
You can tell
Yes.
the entire
Once you put the controller in, do all the negative, positive manipulation. Once you get the final transfer function from input to output, that should have a pole zero diagram that looks like this. Again, zero, I don't care. Zero could be anywhere. I'm not particularly worried about it. But poles have to be in the negative real part.
If you have like multiple inputs, then the transfer function.
Corresponding to each input has to be like that. Yeah. Any other question? Now another thing I want you to notice is the absence of resistor leads to a marginally stable system. What does resistor do in a electric circuit?
Dissipates heat.
Sorry?
Dissipates heat.
Dissipates heat. So what does it do? That's exactly the right point, but it has a specific. It is doing a specific. It is playing a specific role in that system. What is it doing? Losing energy. Okay. So a resistor is essentially losing energy in the system, which leads to a stable system. But if you're not losing energy, so an ideal LC circuit will not lose any energy, and therefore it leads to a marginally stable system. And in the case of unstable system, there is inherent energy. It could be a potential energy, it could be a chemical energy, it could be an atomic energy within the system, which leads to the unstable behavior, because that energy gets converted into a physical quantity like temperature, pressure, and those kind of quantities, and that leads to unstable behavior, which means things blow up in a small amount of time. So in stable system, you have to put some dissipative element which can take the energy from the system and push it into the environment. Okay, so that's how you make a system stable. In the case of nuclear reactors, when you put the control rods in, they become really hot. Okay, but they slow down the neutrons enough so that it doesn't lead to a chain reaction. So that's the dissipative element in a nuclear reactor. So you need dissipative elements in your system in order to make sure that any building up of energy will get dissipated into the environment. Okay, and that leads to stability. Now I'll give you another example of a marginally stable system, which is pretty famous in controls literature. So there was a bridge built in, I think it was in US. It's called Tacoma Narrow Bridge. But I may be wrong, it may not be in US. So you can look up the Wikipedia of this particular bridge. It was built, it was open to public in around 1940s, somewhere in 1940s, and within 4 months it collapsed. And if you think of that bridge, it was marginally stable. So one fine day, the wind was blowing at the right speed in the right direction that led to oscillations in the bridge, and then the bridge snapped. Okay, that's because for some bounded inputs, so for 4 months, you had bound. It was not like the wind was not blowing, right? It was a bounded input, but it didn't lead to unbounded output. But on one fine day, it was a bounded input. The wind was not particularly high, but it was flowing in the right direction at the right velocity. That led to unbounded outputs. And of course, in physical systems, when things go unbounded, it means it breaks, or it cracks, or it has some sort of, it explodes, okay, or it crashes. So those are the kind of things that happens when things become unstable. So in the case of that bridge, it basically broke and it crashed into the river. All right, so I hope the concept of stability is clear. So there has to be a dissipative element in the system in order to make things stable. If you do not have dissipative element, your system could be marginally stable or it could be unstable. Okay, and the dissipative element has to convert energy in one form to some other form, which can then be dispelled to the external environment. All right. Now I want to, so this idea of stability goes back to Maxwell, James Clerk Maxwell, whose wave equations I'm sure you must have studied, and I don't know whether you liked it or not, but I certainly didn't like it. So he came up with these wave equations. So he was also the first person to write the first paper on feedback control systems back in 1850s. And the idea of stability was known by that time, that okay, if you have, not by that time, but around that time in 1860s and 70s, people were working on these ideas, and they figured out that okay, if your poles are in the left half plane, your system is stable. If your poles are on the right half plane, then the system is unstable. and you wanted to make sure that the steam engine is stable, which means that the boiler doesn't blow up because of overheating. So I want to take you back to 1870s, somewhere around 1870s, and I give you a transfer function, okay? So let me write down the transfer function. A complicated transfer function, not a simple one. Okay, simple one, you can do it by hand, like first or second order. So I give you a complicated transfer function, g of s, b m s raised to m plus b0 over a n s raised to n plus a0. I give you a complicated transfer function, and I ask you, is this system stable? Okay, it's 1870s. There's no computer, no MATLAB, no Mathematica, no Wolfram Alpha. Okay, and I want to know whether this system is stable or not. Do we need to find out the poles in order to figure out whether this system is stable or not? No, right? All we need to know is whether poles are in this left half plane or not. That's all we need to know. So we don't need to know individually where the poles are. As long as they are in left half plane, I'm fine, the system is stable. So Routh was a British mathematician. He used to work in Cambridge. I don't know whether he was affiliated with Cambridge University or not. And he came up with an idea which massages these coefficients a0 all the way to an in such a fashion that you can figure out how many poles are in the right half plane. Okay, and that's how you would figure out whether a system is stable or not. So in order to creating that table from which you can derive that information is not very difficult. You can actually do it by hand on the back of an envelope, and you can figure out whether a system is stable or not just based on that table. So that's what we are going to do today. It's known as Routh array. So we are going to study the construction of Routh array and then figure out how many poles are in the right half plane, or how many poles are unstable poles in the system. I'm going to post the proof of Routh's result, the precise mathematical result, on Carmen, but I would completely understand if you don't want to go through it. Okay? It's a long proof. Okay, so I write s raised to n is the largest exponent here. So s raised to n, s raised to n minus 1, s raised to n minus 2, s raised to n minus 3, so on, all the way to s raised to 0. Actually, I should. Okay. I'm going to write an minus 2, an minus 4, an minus 6, and so on. An minus 1, an minus 3, okay, so I have created this first two rows of the Routh array. the third row is going to be minus 1 over an minus 1 determinant of an minus 1, n minus 2, an minus 3. I want to give it a name. Let me give it a name Bn minus 1.
Is that the name of the whole expression right there?
This whole expression. So this is a determinant of a 2 cross 2 matrix. So it's a scalar. I'm going to divide it by scalar multiplied by a negative sign. And I'm going to rename it as Bn minus 1. Okay, here I'm going to name it as Bn minus 3 minus 1 over an minus 1 determinant of an minus 1, an minus 4, an minus 5. Now I need to, and I can keep filling it up in this fashion. So for Sn minus 3, I'll denote Cn minus 1 is equal to minus 1 over Bn minus 1 determinant of an minus 1, Bn minus 1, an minus 3, Bn minus 3, and then I can keep filling up this Routh array in the same fashion. Okay, so how did I construct this Routh array? I created a matrix. So I'm at Sn minus 2. I created a matrix which consists of the first two columns, the first column of the preceding two numbers here. So an and an minus 1, and then the subsequent column, first two numbers, or rather last two numbers, an minus 2 and an minus 3. I take the determinant, I divide it by minus 1 over this quantity an minus 1, that gives me this number Bn minus 1. I do the same thing here. So the first two numbers are still an and an minus 1. The next two numbers are coming from the subsequent column. So this is an minus 4 and an minus 5. Take the determinant and divide it by negative an minus 1. Okay, that gives me Bn minus 3. I can continue doing this. Now when I get to Sn minus 3, now I have to look at these two rows. Okay, the rows. So when I'm constructing the Routh array for Sn minus 3, I have to look at the coefficient of Sn minus 2 and Sn minus 1. So I do the same thing again, minus 1 over Bn minus 1, which is this number here, and then determinant of an minus 1 Bn minus 1 and an minus 3 Bn minus 3. Okay, and I'm going to continue doing this over and over again. Now Routh's result, known as Hurwitz's criterion, which says number of unstable poles is equal to number of sign changes in the first column of Routh array. Okay. So after I have constructed this entire Routh array all the way to S0, okay, I have to go all the way to S0, construct the entire rows, then construct the next row, then construct the next row, and so on, all the way until I reach S0, and then I just look at the first column, okay, look at the first column all the way up to S0, and I see how many times the sign has changed. So if it is positive, positive, negative, 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 negative all the way to S0, then there is one sign change in the first row, which means that there is one unstable pole in the transfer function g of s. Okay? If I look at the first column and I see positive, positive, negative, negative, positive, positive, positive all the way to S0, there are two sign changes, one positive to negative, second negative to positive. So there are two sign changes, which means that there are two unstable poles in this particular transfer function. Okay? And there is a long and tedious proof to show this result, which I'll share with you, but I don't expect you to read it. Any questions on this Routh array? Yeah.
Do we get bonus points if we read it?
Ah, that's a good point. Let me ponder about it over the weekend. Okay?
Thank you.
But how will I know that you have read it or not? Sorry?
Just take our word for it.
Just take your word for
Secret
it?
question on the midterm front page,
Okay.
plus 10 points.
Okay. All right.
I was going to say, can you only say that it's not unstable then? Because can it still be marginally stable if it passes that?
So those are corner cases for that criterion. So we'll talk about it in the next class. Yeah, in this class I don't have time to go over it. But in short, if you have a row that is entire 0, then it implies marginally stable system. Okay. Any other question? Okay. All right. So constructing this array is not a problematic affair even in 1870s. Okay, so if you know the system's transfer function, you can construct this table. It's still a laborious task, but it can be done by hand. And you can ascertain how many unstable poles in the system is just based on this criterion, which is look at the number of sign changes in the first column of the Routh array. Let's try to do it for a very simple system because we don't have much time. Where do I do it? I'm going to do it here. All of you have noted this down. I'm going to erase this. So let's say my denominator, so GS equals to NS over D of S, and D of S is equal to A2 S square plus A1 S plus A0. So I start with S square, S raised to 1, S raised to 0. I have A2, A0, A1, I don't have any term here, so I'm going to write 0 here. What should be the number here? So I have minus 1 over A1 determinant of A2, A1, A0, 0. What is this equal to? So the determinant is 0 minus A1, A0 minus A1. Yeah, A0, that's right. Okay, so the first row is A2, A1, and A0. That's the first row. So when is this system stable? The system is stable if A2, A1, and A0 have all the same sign. So either all positive or all negative. Okay? Then this system is stable. So Routh array says GS stable if and only if A2, A1, A0 have the same sign. Okay, let's look at a third order system. I'm going to erase this, so I'm assuming everyone has noted. Yeah, you have a question? Okay. A3 s cube plus A2 s square plus A1 s plus A0. So I have to start from s cube, then s square, then s raised to 1, then s raised to 0. S cube, what should I write here? A3, and then A1. And then here I have to write A2 and A0. What should the value here be? Let me write down the expression minus 1 over A2 determinant of A3, A2, A1, A0. So that's easy to do. So A1, A2 minus A3, A0 over A2, and I'm going to put 0 here. Okay, I still need to find out the S0 term, so let me try and do it somewhere else. So this is my, let me call this B. Let me call this just B. Okay. So this term is going to be minus 1 over B determinant of A2B and A00, which is equal to A0. Okay, is this clear? The derivation clear? Just follow the Routh table. that I'm trying to that I've written down there. And so what do I get from here? When is a system stable? So let's say A3 greater than 0, A2 greater than 0, A1, A2 minus A3, A0 over A2 greater than 0, and A0 greater than 0. So if all these conditions are satisfied, then it means that system is stable. Actually it is, it goes both ways. So system is stable if these conditions are satisfied. Well, all the signs have to be the same, so I've written it as positive, but you can put the negative sign as well. Like all these signs could be negative. So a system is stable if these conditions are satisfied. If these conditions are satisfied, then the system is stable. So these are all the positive signs, and you could have the same with all the signs being negative. So if those two, so either of those two things hold, then the system is stable. If the system is stable, then either of these two conditions would hold. All right, so that's what I have for today. We have an easy way to figure out whether a system is stable or not. Just construct the array through simple manipulations, and we can easily conclude a system is stable or not. In the next class, we'll talk about some other nuances regarding Routh array and how to determine relative stability of a system. Thank you. Sorry? It happened 11 to 12.